Welcome back, science students. Today we're going to be talking about molecular compounds, how to write the formula for them, how to name them. Now, so far we've only been talking about ionic compounds. Remember, ionic compounds, the name ionic comes from the word ion, which means charged atoms. And they want to be together because of the opposite charges. One part of the compound is positive, the other part is negative, and therefore they want to be together. Well, with molecular compounds, the problem is that they're both nonmetals. Let's take a look and see why this is a problem. Here we've got sulfur, which is a nonmetal, and sulfur has 6 valence electrons. Oxygen also has 6 valence electrons. Both of them want to gain 2 more. Neither one of them wants to give one up to become positive. So what do? Well, instead of transferring electrons and using an arrow to go from one to the other, we're going to share electrons. And how we're going to denote sharing is by circling a pair of electrons. So, in order to try to get to their full orbit, they're going to share. Now, once we've shared one pair of electrons, the way I would count is I would do 1, 2, 3, 4, 5, 6, 7 electrons for sulfur so far. 1, 2, 3, 4, 5, 6, 7 electrons for oxygen. Neither of them are at their full outer orbit. So what do they need to do? Well, they need to share another pair. All right, and now we count 1, 2, 3, 4, 5, 6, 7, 8 electrons for sulfur. 1, 2, 3, 4, 5, 6, 7, 8 electrons for oxygen. So both of them have reached their full stable outer orbit. This now would be classified as a double bond, so 2 bonds between that one sulfur atom and the one atom of oxygen. And that's what a molecular compound is going to look like. Now, because they do things differently, we're going to name them a little bit differently when we write their chemical name down. Let's take a look at how we do that. Okay, so what we're trying to do now is figure out how are we going to name this compound here, which consists of one atom of sulfur, one atom of oxygen, that came together by sharing pairs of electrons. Well, we can't do it the exact same way that we did for ionic compounds because we want to show that it's different, because it is different. So what do? Well, what we're going to do is we are going to use prefixes. And if you remember from English, a prefix is a little part that slaps onto the front of our chemical name. Okay, so we're going to have a prefix onto it. Now the prefixes we're going to use are listed right here. We've got them for 1 through 10, although we're really only going to worry about 1 through 5 for us. Okay, and that's 1 being mono, 2 being di, 3 being tri, 4 being tetra, 5 being penta. Now there are ones for 6 through 10, but they don't tend to come up for us too much. Not that they're any harder. All right. Now, when we're deciding how to name this compound now, what we're going to do is the general rule is we're going to take the name of the first element, the name of the second element. Once again, we're going to change the name of the second element to add I to the end, IDE going on to the end. But instead now, we're going to put a prefix onto both the first element and the second element to indicate how many atoms of that element there are. So, let's take a look at a few examples. First one, we've got N2O3. So once again, we're going to write down the names, only we're going to add prefixes based on the number of atoms. Then with the second element, we're going to add I to the end, just like we did before with the simple ionic compounds. So if I have N2O3, N being nitrogen, there are 2 atoms of nitrogen. We're not going to do any crisscrossing here. So I'm going to write dinitrogen. O being oxygen, I'm going to change the ending to I, so it's going to be oxide. How many? 3, so trioxide. All right, S3F5. What are we going to call this? Well, S being sulfur, so sulfur, but there's 3, so we're going to put tri on the front, so trisulfur. F being fluorine, change the ending to I, so fluoride. There are 5, so pentafluoride. The last one, SO, our good old friend from our example before. Now, I've got sulfur and oxygen, so it looks like it would be sulfur and oxide. And since there's no numbers there, we remember that there's really only a 1 for each. So the prefix for 1 is mono. Now, this is where our rule changes just a little bit. If we have just one of the first element, we're going to skip that prefix mono for the first one, yet we're always going to include it for the second one. So in this case, just going to write down sulfur, and then use mono for the second one, monoxide. Okay, tell you what, I'm going to put up on the screen a few examples for you to try. We'll see how they go. Okay, let's try some examples going the other way. This time we've given you the name, now we're going to ask you to come up with the formula. Now, before what we do is we try to figure out the number of valence electrons, use that to determine the ionic charge, crisscross, reduce if necessary. This is actually a lot more easy. What we've got to do is we look, they tell us the elements, only now we have a prefix that's going to tell us how many of them there are. Now, the big thing is not to crisscross here. So if I have dinitrogen monoxide, I'm going to write down nitrogen. So N, how many of them are there? Di, which is 2. Monoxide, so oxygen, how many? There's just 1. So N2O. Silicon dioxide. Now, this one doesn't have a prefix. Why not? Well, it's the first one, which must mean if it doesn't have a prefix, that it's just 1. So we don't use mono there. So silicon, Si. There's just 1. No need to put that 1 in. I could if I need to, but I don't have to, and I choose not to. Oxygen here, and di, so 2 again. All right, dihydrogen monoxide. This is an element you know very well. H, di, so 2. Oxygen, just 1. H2O, just water. Now sometimes we use that common name water instead, and that's fine. But if we're looking for its chemical name, dihydrogen monoxide is perfectly acceptable. All right, carbon tetrabromide. Carbon, once again, no mono up front, just C. So really just 1 carbon. Tetra, tetra is the prefix for 4, so bromine, Br4. And there we go. Nothing too tricky, just gotta recognize, hey, I'm gonna use the prefixes and they'll tell me how many atoms of that element we have. Perfect. All right, now if we ever give you a question where we're trying to figure out what the name would be when we have chlorine and carbon combining somehow in a molecular compound, the trick is you don't know which one should come first. Now, what you want to do, or how you determine which one comes first, is you're going to decide which one is more metal-like, because typically metals in our ionic compounds always came first. So we want to find out which one's more metal-like. And the way we do that is we figure out which one is closer to the periodic table here on the metal side of the periodic table. Because we know the metals are over on the left-hand side, the non-metals on the right-hand side. So when we look at them, whatever one is further to the right is going to be our element that comes first. If they're both in the same column, the one that is lower down on that column is going to be considered more metal-like, and therefore will come first in the ionic compound. So if we have chlorine and carbon, what we're going to do is carbon would come first, chlorine would come second. So in this case, what I'd have to look at is how many bonds do they want to make. So again, I'm going to kind of draw on our knowledge of valence electrons here. Carbon wanting to make 4 bonds, chlorine wanting to make just 1. So what we're going to have is carbon coming first because it's further to the right on the periodic table, only wants to make 4 bonds. Chlorine wanting to make 1 bond, and in this case we will crisscross. The 4 will come down, the 1 will come down. Now we're not crisscrossing charges, but rather the combining capacity. So CCl4, and if we were going to name this thing, it would be carbon tetrachloride. Again, changing the ending to IDE and putting our prefixes on. So there we go. Okay, the last type of naming we're going to do with molecular compounds are for compounds that we use on a regular basis. And society's given them a name that we commonly use and that's generally a little more preferred or can be used in place of their chemical name. So for example, we know this is dihydrogen monoxide now, but instead we can just call it what we know it as water. H2O2, you probably have some in your medicine cabinet right now at home. This is hydrogen peroxide. Okay? O3. Okay? Your hot tub might use this to keep it clean. This is ozone. Okay? CH4. This is methane. Our last one, NH3. This is ammonia. Okay, when we have diatomic molecules, in other words, hydrogen, for example, bonding with itself to form an H2 molecule, generally these are gases, and we're just going to name them as such. H2, we're going to call this hydrogen gas. O2, oxygen gas. And then Cl2, we're just going to call that chlorine gas. Not too tricky. So when you see something that's bonded with itself, there's a good chance it's a gas. Cl2, chlorine gas, O2, oxygen gas, and so on. All right? So that's the last type of molecular compounds we'll worry about, either the gases or just common chemicals that we use on a daily basis that we've given it a name historically. All right? There you go. That's molecular compounds.